A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. In today's lecture, we will be talking about temperature, heat, and the first law of thermodynamics. This lecture is a part of the lecture series from the course of thermodynamics, having the course code of PHY331. Basically, we need to understand the concept of temperature, heat, and the first law of thermodynamics in this lecture. Before starting the concept of heat and temperature, we need to know the zeroth law of thermodynamics. That is actually gives us the concept of thermal equilibrium. And according to the zeroth law of thermodynamics, if two bodies A and B each are in thermal equilibrium with a third body T, so what happen then? A and B are in thermal equilibrium with each other. Here in this figure we can see that there are two bodies, one is A and other is B, and T is considered to be a third body. In the first case, A is brought in thermal contact with body T, and it is found that both are in thermal equilibrium with each other. Then independently, the body T is brought in thermal contact with body B, and it is found that both the bodies are in thermal contact with each other. So it is in thermal contact with each other, and as a result of this thermal contact, these are in thermal equilibrium with each other. And finally, we conclude from the zeroth law of thermodynamics that the body A and body B are in thermal equilibrium with each other. So this is actually called as the zeroth law of thermodynamics, and it gives us the concept of temperatures. So how we can measure the temperature of something? So temperatures, there are different thermometer for measuring the temperature. We have a gas thermometer, we have mercury thermometer, different thermometers. So constant volume gas thermometer consists of a gas bulb, it is shown here, and that is connected by a tube to a mercury thermometer, to a mercury manometer. So what happened, by raising and lowering the reservoir R, the mercury level in the left arm of the U-tube, of the U-shaped tube, can be brought to the zero of the scale to keep the gas volume constant. And what happen when the temperature of any body is in thermal contact with the triple cell bulb is? So we can use this equation for that. And if the atmospheric pressure is P naught, so for any particular pressure, P will be equal to P naught minus rho GH. So therefore we can find the temperature that T is equal to T3 P divided by P3, and we can find out its values. We have different scales for measuring the temperatures. Normally the three scales are, the one is the Celsius scale, the Fahrenheit scales, and the Kelvin scales are the normal scales that are used for measuring the temperature. So normally in Celsius scale, the temperature are measured in degrees. So the Celsius scale has the same size as the Kelvin scales because it has 100 divisions. So the zero of the Celsius scale is shifted to a more convenient value than absolute zero. Temperature measure in one scale can be easily converted into other scales, and there is some equation for that. Just like if we want to make the conversion between Fahrenheit and Celsius scale, so we can use this equation for that. So it's very easy for us to use this equation and convert the measurement done in one scale system into and convert it into other scale systems. We have some example for that. If some temperature is given to us, we can easily convert it into other. Just like in this sample problem, we have a temperature that is minus 14 degrees Z. Z is considered to be as any scales. So we need to convert it into some other scales, and then we need to find out its values. So what happen when temperature is below the freezing point by 84.0 degrees Z, so it must be below the freezing point. So we can use this equation to find out the temperature in Fahrenheit. So one temperature is given, and we can use the linear equation to convert it. We use the simple equation that is mentioned here in this to convert the temperature. Thermal expansion. Normally when we increase the temperature of body, so it expand, and this is called as a thermal expansion. So it is further divided into two type. One is called as linear expansion, another is called as volume expansion. In case of linear expansion, if the temperature of a metal rod of length L is raised by an amount T, its length is found to increase by an amount so the temperature is the change in length is given by del L is equal to L alpha del T, where alpha is the coefficient of linear expansion. Here in this table, some coefficient of linear expansion of different material is given. We have this value for the substances just like oil, lead, aluminium, brass and copper, concrete, and similarly for steel as well we have the value of alpha. So this is room temperature value except for the listing for ice, that is at 0 degrees C. Thermal expansion is has the other category that was called as a volume expansion, and in case of volume expansion would happen, we see that in case of volume expansion, when we increase the if the temperature of a solid or liquid whose volume is V is increased by an amount dt, so the increase in volume is found to be del V is equal to V beta del T. Del T is actually del T, where B is the coefficient of volume expansion over here, and the coefficient of volume expansion and linear expansion for solid are related to each other by an equation that is equal to beta is equal to 3 alpha, where beta is the coefficient of volume expansion and alpha is the coefficient of linear expansion, and both are related to each other. We have thermal expansion, in which we have the anomalous effect of water. Water has anomalous expansion, and that is different from the normal liquid. The most common liquid, water, does not behave like other liquids. So above 4 degrees C, water expand as the temperature rises, as we normally expect from all the materials. But between 0 and 4 degrees C, however, water contracts with increasing temperature. So thus above 4 degrees C, the density of water passes through a maximum. At all other temperatures, the density of water is less than this maximum value. So thus the surface of ponds freezes while the lower water is still liquid, and this helps the life inside the ponds or lakes to be going on, because if the whole lake will freeze, so it will be a great problem for the life or for that is inside the pond. So that is why it is going on. So this is actually the anomalous expansion of water that is useful for the so this is something about the anomalous expansion of water, where ponds the surface of the ponds freezes while the lower water is still liquid. Temperature and heat. So heat is actually the energy transfer between a system and its environment because of the temperature difference that exists between it. Because we have normally the temperature flow from a body at higher temperature, and the heat flow from a body to at higher temperature toward the body at lower temperature, and this flow of heat continue until both the body achieve the same temperature. So this is something called to be a heat that is actually that is transferred between the bodies by the virtue of their temperature difference. How we can describe the units of heat? Normally the calorie was actually defined as the amount of heat that would rise the temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees C. In a British system, the corresponding unit is called as BTU, that is called as British thermal unit, and it is defined as the amount of heat that would raise the temperature of 1 lb of water. of water from 63 degree Fahrenheit to 64 degree Fahrenheit. So normally in SI system the unit of heat is joule, and there is some relationship between the joule and the BTU, British thermal unit, and and this is equal to 1 calorie is equal to 3.968 multiplied by 10 to the power minus 3 BTU, and that is equal to 4.186 joule. The absorption of heat by solids and liquids, so that is actually called as heat capacity. So heat capacity of an object is the proportionality constant between the heat that the object absorbs or loses and the resulting temperature change of that object, and Q in that particular equation Q is equal to C del T. We can also write the equation to be Q is equal to C into Tf minus Ti, where Tf and Ti are the initial and final temperatures. So heat capacity is the unit of energy per degree or energy per Kelvin. Specific heat, when we specify the mass of the object or the matter in any particular case, so the same heat capacity is considered to be as a specific heat. So the specific heat is actually the heat capacity per unit mass. So it refers not to an object but to a unit mass of the material of which the object is made, and so for that we have Q is equal to C m del T, and when the quantities are expressed in moles, so that is called as molar specific heat. The same specific heat when the quantities are expressed in mole, so that is called as a molar specific heat. We have the values of the molar specific heat at room temperature for different materials, leading from starting from the lead to water. We have heat of transformation and heat of vaporization and heat of fusion. That is actually the transformation of a substance between different phases. So that is actually the amount of energy per unit mass that must be transferred as a heat when a sample completely undergoes a phase change. So that is actually called as a heat of transformation, and heat of transformation is represented by L. So when a sample of mass m completely undergoes a phase change, so the total energy transfer is equal to Q is equal to Lm. We have another thing that is called as heat of vaporization. That is actually the phase change between liquid to gas, and the heat of transformation in this particular case, when we transform a substance from liquid to gas, that is called as heat of vaporization. Another term is called as heat of fusion, and that is the phase change between solid and liquid. When we change the phase of a substance from solid to liquid, then the heat required for that particular phase transformation is called as a heat of fusion. We have heat of transformation for different material, that is the heat of vaporization and heat of fusion. We correspondingly call as a melting and boiling. So its values are given over here. First law of thermodynamics gives us the concept of energy of any particular system, internal energy of a system, and it says that internal energy of a system tends to increase if energy is added as in the amount of Q, and it decreases if energy is lost by doing some work. So internal energy is equal to dq minus dw. This is actually called as the first law of thermodynamics. The q minus w is the same for all processes. So we have different combination of q and w, and therefore we have different sort of application or process of first law of thermodynamics. Some are adiabatic process, and in case of adiabatic process, it the total amount of heat enters or leaving the system is equal to 0. The Q amount is equal to 0, so the work is done at the cost of internal energy. So that is actually negative work. We have constant volume processes. In that case, when the volume is constant, so no work is done. So P dV is equal to 0 as a result W is equal to 0, and the total heat provided to the system in this particular case is used in increasing the internal energy of the system. We have some cyclic processes, and that are actually the processes after a certain interchange of heat and work, the system is restored to its initial configuration. So no intrinsic property of their systems, and in this case the internal energy of the system is considered to be equal to 0. When it is equal to 0, then Q should be equal to W. We have some free expansion process. In case of free expansion, is a type of adiabatic process in which no heat enters or leaves the systems. No heat is transfer occur between the system and its environment, and no work is done on or by the system. So Q and W both should be equal to 0. So change in internal energy should be equal to 0, and this is called as a free expansion. We have some specific values for some specific cases of first law of thermodynamics, where we have adiabatic, constant volume, closed cycle, and free expansion processes are the constant. We have some example from the first law of thermodynamics where we can find out the work done, and this is simple example where some values are given. We can find out the work done. Heat transfer mechanism. There are several heat transfer mechanisms by which heat can transfer from one place into another place. So normally we have conduction, convection, and radiations, and different processes are used or responsible for that. And in some cases we need medium for the heat transfer, while in some cases we don't need any medium. Just like in conduction process, we need a medium to transfer the heat from one place to another place. Just like we have a slab that have particular area and thickness, and that is temperature is increased, and that is present at high temperature. So what happen? A metal rod is placed in between it, or in other words, both the objects are brought in thermal contact with each other. Maybe a rod is placed in between the two objects. So what happen? The heat will transfer from the object at high temperature toward the object at low temperature, and this conduction process will and depends upon the heat transfer per unit time, and that is actually called as the conduction process. So if we simplify the equation, we have K, that is called as the thermal conductivity, and the thermal conductivity depends upon the quality of the material. We have different values of thermal conductivity for different materials. So if it has good thermal conductivity, so it will have very good quality of thermal conductions. Here we have some of the example of the values of the thermal conductivity of different metals. So just like we have stainless steel and iron, brass, and window glass, so the thermal conductivity of these materials are mentioned here. The other process of heat transfer is the conduction we already discussed, and its value is expressed here. We have other thing that is called as the heat transfer. We have convection, but before convection we also need to know the radiation as well. Radiation is also a way by virtue of that heat can transfer from one place to another place. Just like from sun, heat is transferred to the surface of earth with the help of radiations. So in this slide we will discuss the convection process. So in convection, energy also transfers between different objects or between different bodies, and in that case, along with the transfer of energy, mass is also transferred. So energy transfer occurs when a fluid such as air, water, or some other fluid comes in contact with an object whose temperature is higher than the temperature of that particular fluid. So that particular fluid will move, and that will take the heat with itself. So the temperature of that part of the fluid that is in contact with the hot object increases. So that is normally the case, and the fluid expands and it becomes less dense, it will move up. So that is why the colder fluid will be brought into thermal contact to that particular hot object. So what happen, that is also its temperature increases, so the surrounding cooler fluid flows to that particular place, and then continuously the whole fluid temperature is increased. So this is a way how heat is transferred between some objects. So we have radiation, convection and conduction process normally used for that. So this is something about general discussion about temperature and the convection and radiation process. Thank you very much.